prepare to be amazed. I am going to move this ball to this table without touching it. I'd love to tell you how that's done, but a good magician never reveals his secrets. It's a good thing I'm not a good magician. That works because we are right now in a gravitational field. And a gravitational field is a region where a force acts on a mass. So right now, that force is trying to pull this mass towards the centre of the Earth. And so if I let it go, it falls. And an electric field is really similar to that. An electric field is a region where a force acts on a charge. So if you imagine that this is a charged particle, and when I click my fingers, I'm going to set up an electric field right across the screen. It will feel a force due to that electric field. Let's see what happens. It's quite a strong field. Okay, so right now I'm having to do work against the field, right? And pushing it towards the side of the electric field. If I don't, then, well, it's being forced this way. So this is what happens when I stop doing work. Okay, I'm going to turn the field off now. If this was a negative charge, then obviously it would experience the force in the opposite direction, assuming that we didn't change the field. Like this. Right, off. Okay, fed up of that. We can represent an electric field using what we call electric field lines. These lines show the direction that a positive charge would be forced if it were put at that position. This type of field is called a radial field. That's what you get when you have one point charge in the centre. And that's all there is. So if I were to put a positive charge right here, it would be forced that way. Or here, it would be forced that way. The same thing works for if you have a negative charge in the middle, right? Put a positive charge there, and it will go towards the negative charge. Or rather, it will be forced towards the negative charge. Negative charges are a bit rebellious, and they would move in the opposite direction to where the arrows are pointing. Okay, so the arrows point in the direction that a positive charge would be forced. Now that's quite important, because that's not necessarily the direction they will move in. If you imagine that I'm a positive charge, and I start running at you, but then a field gets produced across the screen, just like we had before. Now, if I'm running towards you, and someone pushes me in this direction, I'm not going to instantly go, right? What I'm actually going to do is I'm going to probably move off at a diagonal to where I was going. I was going that way, I got shoved in this direction, and so I'll probably end up getting pushed out like that. Okay? So the field lines there are not necessarily the direction that the charge would move, but it's the direction that a charge would be forced in. Let me now show you an example of a radial field. And so for that, we use our old friend, the Van de Graaff generator. Now you might notice something rather odd on top of this Van de Graaff generator. Yes, it's a Barbie. And as you can see, this Barbie is at the height of fashion. Well, second only, of course, to myself. But nevertheless, I think it's important that we show her respect. Anyway, what I've done is I've rammed a giant metal spike in her ankle, right here. And so that's going to allow her to be fixed on top of this Van de Graaff generator. When I turn this on, the hope is that her hair will spike up on end in a rather ludicrous fashion, which will represent a radial field. Okay, so right now all of her hair is acquiring a charge, and because it's all the same charge, every strand of hair is trying to repel from all the other strands, which is why it spikes up on end. The hair lines that you can see are a little bit like the electric field lines that you saw on the board. Her head is like the point positive charge, and her hair is like the electric field lines. Okay, I think we've shown her enough respect. Thanks. But what happens if you add more charges? How would an electric field change? Well, there's a few different scenarios that you need to be familiar with. And the first one would be if you had a positive charge and a negative charge. Okay. Now, the way I like to think of this is imagine you are a positive charge and where you would be forced. If you're right here, you're obviously going to get forced continually away from that positive charge forever. But if I add another negative charge over here, then eventually you get close enough to that negative charge and you start feeling a force of attraction towards it. Which is why the field lines curve round like that. If you compare that to adding another positive charge to this diagram, it's the opposite. Again, you start off being repelled by this positive charge, and at some point you start to feel the repulsion from that charge too. And so the only way for you to be forced is directly up, equally away from both the charges. And the same happens at the bottom side of this picture. The last type of field you need to know about is something called a uniform electric field. So if you set up your positive charges in a line, like you would on a metal plate for instance, and you set up your negative charges on a line as well, again, a bit like a plate of negative charges, then you should see that the field in the middle has straight lines. This is called a uniform electric field. So called because it doesn't matter where you put a positive charge in between these two plates, it will feel the same amount of force in that direction. And I can show you a parallel field, or rather a uniform electric field, right here. Now to get this working, I just need a small voltage. It's about 4,500 volts. The red end, this plate here is going to be positively charged, right there, and this side is going to be negatively charged. The little ball in the middle has got a metallic paint, and that means it's able to take on any charges that it comes into contact with. So I'm going to, first of all, nudge it to that plate. Now when it hits the positive plate, it takes on those charges and then is instantly repelled from the positive plate. It's like, thanks for the positive charges, yuck. It then gets attracted towards the negative plate, gets rid of the positive charges, and takes on the negative charges. At which point it immediately goes, yuck, and gets repelled from the negative plate. And this is why we get, ultimately, a shuttling ball. It's taking charges from one plate and ferrying them, or bringing them, to the other plate. It wouldn't matter where the ball was along these two plates, it would feel the same amount of force, because the electric field is uniform. Okay, time to exit. Just doing this for you, okay? So I'm going to activate my electric field. Don't know which way it's going to be, right or left. Let's see. Oh! What the heck? No!